This video explores how to translate the time-independent Schrödinger equation for a one-dimensional particle in a box from continuous calculus into discrete linear algebra using Python. The objective is to numerically solve the time-independent Schrödinger equation for a particle in an infinite potential well, where the potential V of x is 0 between 0 and L and infinite otherwise. We are looking at a particle confined within a one-dimensional box. Our goal is to numerically solve the time-independent Schrödinger equation for this infinite potential well, assuming constants h bar equals 1, m equals 1, and L equals 1. The core of this problem is the time-independent Schrödinger equation. The kinetic energy operator, hat t, represents how the wave function's curvature changes. We seek the total energy E, which is the eigenvalue, and the wave function psi, which represents the state of the particle. The computational challenge is moving from continuous calculus, which computers cannot directly process, to discrete algebra. We solve this by using the central finite difference approximation, discretizing the spatial domain X into n finite points. For the particle in a box, the total energy Hamiltonian, hat h, simplifies to just the kinetic energy operator, hat t. The key is to convert the second derivative, representing wave function curvature, into an algebraic form. The finite difference method allows us to discretize space. We approximate the second derivative using the values of the wave function at the point of interest, psi, and its immediate neighbors, psi-1 and psi-i plus 1, all divided by the squared spacing delta x squared. This approximation leads to the Laplacian matrix. The main diagonal contains -2, representing the -2 psii term. The off-diagonals contain 1, representing the SII1 and SII plus 1 neighboring contributions. Boundary conditions are implicitly excluded. The first step in code translation is setting up the physics and math constants in Python. We define the reduced Planck's constant, mass, box length, and the number of grid points, which then determines our grid spacing delta. Next, we build the Hamiltonian matrix. We create the diagonal and off-diagonal arrays, combine them into the Laplacian matrix, and then multiply by the constant factor to form the full Hamiltonian matrix, hat h. The resolution involves solving the eigenvalue problem, hat h psi equals e psi. We use NumPy's np.lena-lg.agagh backquote function to calculate the eigenvalues or energy states and the eigenvectors or wave functions. We specifically isolate the lowest 3 energy states. Verification shows the success of the method. The numerical energy eigenvalues perfectly match the theoretical, analytical solutions derived from the formula, proving the validity of the finite difference method. Finally, the visual payoff, plotting the wave functions. We see the first 3 energy eigenfunctions, n equals 1, n equals 2, and n equals 3. These wave functions drop to 0 at the boundaries, fulfilling the physical constraints of the infinite box. Our numerical approximation must match the analytical baseline provided by continuous calculus. This formula provides the exact energy solutions, against which we check our Python calculated values. In summary, the pipeline converts the physics of a differential equation into mathematics using a finite difference grid. This allows for computation using a tridiagonal matrix and Python arrays, leading to the result of solved eigenfunctions. By treating space as a discrete grid, we use linear algebra to solve complex quantum mechanics.